Okay, problem number 4. If a gaseous mixture is composed of, alright, I've got 3.45 grams of argon and 5.55 grams of helium in an evacuated, meaning there's just no gas in there, 3.04 liter container at 25 degrees Celsius, what will be the partial pressure of each gas and the total pressure of the container? Okay, this is new, so partial pressure. When I hear partial pressure, immediately in my head I start thinking Dalton's law of partial pressure. So I'm going to put that down first, actually. P total, this is Dalton's law here, is equal to the pressure of the first gas plus the pressure of the second gas. And if there were more, that's why I'm putting this ellipsis, if there were more you would add them in as well. But we just have two gases here, I can already tell that. Argon is gas number 1, helium is gas number 2. Okay, so if I want to know the partial pressure of each of these, or rather if I want to know the total pressure, all I have to do is add those two pressures together. But if I look back up here, I don't have those two pressures. So what I have to do is find it. And so I'm going to kind of split my page in two. Let me get a different color here. So argon's going to be pink. So this is argon. Let's put down what information we have here. I know that I have 3.45 grams of argon, and grams, what can that be converted to? Well, of the variables I know of, I mean, we can do P, we can do V, N, R, T. N is the closest one. I can actually convert grams to moles, so I'm going to come back and do that later. So the N is this grams here. And I know that it's in a 3.04 liter. Liters is a measurement of volume. So volume is equal to 3.04 liters. And the container is at 25 degrees Celsius. What is degrees Celsius a measurement of? Temperature. Got 25 degrees Celsius. What will be the partial pressure? So I want to know the pressure of that. And that's actually what I'm trying to find. And then the last thing to do is to kind of evaluate this information. I've got pressure, temperature, volume, moles for N. I don't have any changing variables here. I don't have like V1, V2, I don't have T2, T1. So I know I'm not using that combined gas law. The P1, V1 equals P2, V2, anything like that. Actually, what I'm going to be using is the ideal gas law, which is PV equals nRT. And the way I figured that out is I've got all of these variables. The only one left is R, and I know that one. It never changes. R is equal to 0.0821 liters ATM over moles Kelvin. And so right now I can find out the pressure of argon. Before I actually do that, let's write out the same information for helium over here. So helium is going to be this blue color. And I've got N is equal to 5.55 grams. And then the rest, it's in the same container, so the rest is going to be the same, 3.04 liters. Temperature is still 25 degrees Celsius. The pressure is, again, still what I'm trying to find, and then we have R because that never changes. It's 0.0821 liters ATM over Kelvin moles. Alright, and I'm actually going to scroll this down a little bit here, so I've got some space to work. Okay, so let's go back to our pink color here. So I need to see, are all of these units the units that I need? So liters, I'm always basing it off of this R constant. These are the units I need. Liters, yep, that's what I have for volume. Pressure, ATM, that's what I'm going to find, so I might as well just put ATM here. Moles. Moles is for N, so actually that one is not right, and so I'm going to have to do a little conversion here. I need to find moles of argon. And so I'm going to take this unit and move it down here. Grams of argon is equal to moles of argon. Any gram to mole ratio, what number goes with moles? Should be 1, because we're trying to find how many grams are in 1 mole. And so now what you have to do, this grams of argon, you got to go find your periodic table, and I'm doing the same thing. So I'm looking for argon. Okay, and so this is going to be 39.95. 39.95 grams. And let's put that into the calculator. 3.45 divided by 39.95 equals, and this number is pretty small, it's 0.08636. Alright, and then the last one, K, for temperature, Kelvin. I need this to be in Kelvin, so add 273 is equal to 298 Kelvin. So now I'm ready to plug this information into PV equals nRT. So pressure is what I'm trying to find. So pressure is obviously just P. And I'm going to put down here that the pressure of argon, PR. Times the volume. The volume is 3.04 liters, is equal to N. I just found N, which is 0.08636 moles. This is getting a little messy there. Now I'm going to put in my R value, which is 0.0821 liters ATM over Kelvin moles. And then the last part of this equation here is going to be, sorry, I'm going to go back and fix that. It was kind of bothering me. Temperature is 298 Kelvin. And so really now I'm just simplifying this information. So I'm going to start on this side over here and simplify that first. So 0.08656 right here times 0.0821 times, excuse me, get rid of that, times 298 Kelvin. And so, like I've said before, I'm going to leave this number in the calculator, but just so that you can see what it looks like, it's 2.1177, and my units, moles cancels here, Kelvin cancels here, so my units that I'm left with are just liters ATM is equal to, and then still this pressure of argon times 3.04 liters. And so I want pressure by itself. That's the number, or the variable I'm trying to solve for. To get rid of this 3.04, any number divided by itself can cancel out. Whatever I do to this side of the equation, I'm going to do to the other side of the equal sign. So divided by 3.04 liters. Liters will cancel out, and so my units will be ATM, which is, like, that makes sense. That's what I should have for pressure. So divided by 2.1177 divided by 3.04 is equal to, so the pressure of argon is equal to 0.6966 ATM. I'm going to make this significant figures, and I'm basing this on temperature. So the pressure of argon is actually 0.70 ATM. And I'm not actually done yet, because if you'll remember, we've got all this information about helium over here. So I'm going to scroll and move this over so we've got some space to work with here. And let me switch back to my blue here. So now I've got to do the exact same process for helium, because I need the pressure of helium. Well, up here, so let's go through these units. Liters. Yep, I've got liters for volume. ATM for pressure, that's what I'm going to be finding. K, Kelvin for temperature, so I need to add 273 is equal to 298 Kelvin. And then moles, this is not moles. I need to convert this. So I'm going to put grams of helium down here. That's not exactly the best handwriting I've ever done. Up here is going to be moles of helium. That's what I'm trying to find. Moles of He. And so same thing, moles He up here. Anytime you have a gram to mole ratio, what number goes with moles? It should be 1, because we want to know how many grams are in 1 mole. And that's 4.00 grams. And so right now I'm going to do 5.55 divided by 4.0, and the moles of helium is 1.3875. So I want to ask you a question real quick. If the moles of argon were 0.08 compared to moles of helium is 1.38, which pressure do you think is going to be higher? And hopefully what you're thinking is, if there's more gas here, so there's more moles, it's probably going to have a higher pressure. And so we're going to write that out and see what we get. So we're going to do again PV equals nRT. So the pressure is ATM. So I'm going to put pressure of helium times volume. The volume is 3.04 liters. The N, the moles, we just found it. It's 1.388 moles times our ideal gas constant, 0.0821 liters ATM over mole Kelvin times, and then our temperature was 298 Kelvin, room temperature. So I'm going to simplify this side first because there are no variables over here. It looks to me a little bit easier. So 1.388 times 0.0821 times 298 Kelvin is equal to, so I'm getting here 33.946, and I'm leaving that number in the calculator, but I just want to write it here so you can see it. Moles cancels here, Kelvin's on the bottom here and it's on the top here, so it cancels out. So the units I'm left with are liters ATM is equal to 3.04 liters times the pressure of helium. And pressure of helium is what I'm trying to find. I want that variable by itself. So I'm going to divide by 3.04 liters. Any number divided by itself cancels out. Anything I do over here, I have to do on the other side of the equal sign. 3.04 liters. So 33.9, and like I said, that I actually just still in my calculator, divided by 3.04. So the pressure of helium, actually so I'm going to do this kind of over here, and you'll see why in a second, but the pressure of helium is equal to 11.166 ATM. Like I said before, I only have 2 significant figures, so the answer is going to be 11 ATM. And so let me scroll and show you. So here I've got my 2 pressures. This is the pressure over here of argon. This is the pressure of helium. Now I can't. Oh, it's 1 significant figure. Whoops. That's unfortunate. So this actually has to be rounded down to 10 ATM. And this over here is not correct. Was it? No, I'm sorry, it was 2. Shoot. So it still is 11. Sorry, I'm getting a little confused here. Okay, so if you remember back to that original equation, so this is all the work we just did, it wanted the partial pressure of each gas, and we just found that, helium and argon, but it also wants the total pressure. And so that's where this equation came in. P1 plus P2 equals total pressure. That was our Dalton's law. So I've only answered 2 out of 3 questions. This is the partial pressure of argon, this is the partial pressure of helium. In order to find P total, I need to add 0.70 atms for argon plus 11 atm for helium, and so the total pressure is going to be 11.7 atm. Unfortunately, so I don't think I made this the best question in the world because I need 2 significant figures, and so I need to round this one as well to 12 atm for total. And so going back to that question about, so argon had such few number of moles, let me scroll this up a little bit, had such a small number of moles, helium had a much higher, and we were saying, you know, does that affect the pressure? Well, we found out, yes, the pressure of helium should be much higher, and it makes up almost all of the pressure